So the next thing to see is we have finished the links, broadcast link and the point-to-point link, and then broadcast links. Now let's look at another issue, which is bridging. That if you have tried to use broadcast link to link many stations together, and still you have the scalability issue that you can accommodate too many stations on one broadcast link. You can only accommodate 2 stations on a point-to-point link, but you can accommodate many stations on a broadcast link. But that many couldn't be too many. You can accommodate, say, 100 stations on a broadcast link, but probably no more than hundreds. You can go beyond hundreds on a broadcast link. So then you would have a broadcast link here, broadcast link here, broadcast link there, and then they form a broadcast domain or collision domain, and they form a network. And if you want to send a frame from this network to another network, from this broadcast domain to another broadcast domain, or from this collision domain to another collision domain, then you need something called some internetworking mechanism. And there are 2 internetworking mechanisms. One is called bridging, one is called routing, which we will describe in the next chapter. Bridging we will describe here. Then what's the difference between bridging and routing? You need to internetwork links together. What's the difference? The bridging says that you can only rely on information at the link layer. You can't rely on information on the other layer. So the way to differentiate bridging and routing is bridging. You look at the MAC header or the link header or the MAC address. However, routing look at the network address, which is IP address. So bridging, you wouldn't look at the IP address. You look at the MAC address, the 6-byte, 48-bit hardware address, right? So you look at that address to make your bridging decision. Okay. And here we will look at 3 mechanisms that compose, that is constitute the bridging, which are self-learning, spanning tree protocol, and VLAN. We look at this figure as an example, where you have 2 switches or 2 hubs. Okay, so these are connected together. They form a broadcast link or a broadcast domain or collision domain. Here it's they form another broadcast domain. Maybe well, first of all, I'm not sure whether I described the difference between broadcast domain and collision domain. Did I? No. Okay. So what's the difference between? In order to interconnect these together, we have a hub that is actually internal. It's a bus. So and connected together. This if I have 24 ports, I can connect 24 stations. So then it's internal. It's a bus. So it's a broadcast domain and also a collision domain. So if any station send a frame, it'll be heard, it will be received by the other station, all the other stations. So it's a broadcast domain. And it's also a collision domain, meaning if 2 stations send frame at the same time, they will collide. they will collide because internal is a bus. It's a bus. It's a bus, so it will collide. So they run CSMACD to resolve the collision, right? Fine. And later on, they try to separate collision domain and broadcast domain by Ethernet switch. Internally, it's not a bus anymore. It's a switching fabric. And the easiest way to design a switching fabric is design it as a memory. So the input port, so if a port has incoming frame, it will be written into a memory space. And if you want to transmit, you would grab from the memory and transmit at another port. So the incoming will be incoming frame will be written into the memory, and outgoing will be read from the memory. Okay, so internally it's a memory, or it's a switching fabric. There are other possibilities to design a switching fabric, and memory is one of them. Okay, but internally it's not a bus. So so if a station sends a frame, would it collide with the other station? No, it won't. So as we say that Ethernet has become a point-to-point link. So one port is itself a broadcast link. Sorry, a collision domain. So if we have 24 ports here, it will be 24 collision domain. Each of them will be a collision domain. If I connect, this to one port, then this will be a collision domain. This will be a collision domain. But this will be 24 collision domain. So I have 24 collision domain, meaning different ports would not collide with each other. So that's a 24 collision domain. However, I still want all 24 ports to be within one broadcast domain. What does that mean? If a station sends a frame, a broadcast frame, that broadcast frame should be forwarded to the other 23 ports. The other 23 ports should receive the broadcast frame. And remember that if we want to send a broadcast frame, the MAC address should be what? The destination MAC address should be what? All ones, right? It's a 6 byte, 48-bit MAC address. Should be all ones. And then the switch will know, okay, this is a broadcast frame, and I should forward to all the other ports, right? All the other 23 ports. So, but if it's a hub, it's natural. The switch does not need to do anything. It will broadcast because it's internally it's a bus. So if one station sends a broadcast frame, it will be automatically forwarded, automatic broadcast to the other station, and the other station would receive that frame because it's a broadcast frame with the all ones in the destination MAC address. So for hub, it's effortless to send a broadcast frame, but for switch, it's not effortless. You need to the switch needs to forward, do something extra to forward the frame, to duplicate the frame to the other 23 ports, right? So when you separate the collision domain into 24, from one collision domain into 24 collision domain by offering a switch, Ethernet switch, instead of Ethernet hub, you need to do something extra to unite the 24 port into one broadcast domain. Okay. So when you are in a broadcast domain, if someone sends a broadcast frame, it needs to be forwarded, duplicated to the other port. Is that clear? Okay. And And that's something extra that the switch needs to do. Okay, so now we are clear about the idea, the difference between collision domain and broadcast domain. So a hub is a broadcast domain and also one collision domain. Okay, but a switch is one broadcast domain but separate collision domain, right? So see, if this station wants to send a frame to this station, okay, the source is this and destination is this. So this frame send a frame with the destination MAC address of this to a certain port. And then the switch needs to figure out where to forward the frame. Because this is not a broadcast frame, this is a unicast frame with a MAC address of this. So the destination, the switch needs to figure out where the station is, where the destination is. And it knows this by looking up a table, an address table. So it got lucky. It find this MAC address. Okay. So this guy, this MAC address, this adapter card is on port number 2. So the switch will forward the frame to port number 2. Port number 2. Then it forwarded correctly. Then the question you should ask is, how come the switch would get the table entries of this? How come the switch would have this entry? How come? That's because this station talked to the switch before. It talked to the switch before. So the switch would do something like this. For any frame I receive, I would check its source address, not just destination MAC address. I would check the source address. So that, okay, because this guy has sent a frame to me before, and I check the source address of the frame, and I find out that, okay, and I find it, okay, this MAC address, it belongs to port number 2. So I insert this entry into the table here. So I learned that, okay, this guy come from port number 2, and I record it in my table. Okay, so I do the self-learning on source MAC address for every frame I receive. Of course, the frame has a destination, so I look up the table again to see whether its destination is there. If it is, then I know which port the destination is. Okay, so when as a switch, I need to look at both source MAC address and also destination MAC address. And I look at the source MAC address in order to do self-learning, to learn the table. And I do I check the destination MAC address in order to do the forwarding, in order to forward a frame. Okay, so if you keep doing that, it's likely if the station are active, then they will definitely need to send frames. Say in this if we have 1,000 station in the whole topology, then eventually I will learn 1,000 cars, 1,000 adapter cars, their address, and I will know where the port number are, where they belong. So if a frame destined to one of them, I look up the table, I would find the port number to forward the frame. So that's called self-learning, and it's transparent to the stations. Transparent in a way that it's plug and play. The station does not know. The station does not need to do anything to tell the switch to do the job. The switch will do the self-learning by itself. So there is no configuration needed. The station does not need to configure on the switch, telling the switch, okay, this is my MAC address. No, they don't. They don't need to tell the switch. The switch will learn by themselves, and it's self-learning. And how about if this station wants to send a frame to this station, then it's across multiple switch or multiple hubs. Okay. Then if I send this frame destined to that, and the switch got it, now it check the destination MAC address, and then look up this table and find none. I couldn't find a MAC address of that one. Then what would happen is that if I don't know where it is, I would fraud. I would duplicate this unicast frame to all the other, say, 23 ports. So one of the the port, so this port would also get the frame, right? It would also get a frame. And then when it's sent here, it'll be received by this. If it's a hub, then you'll be received directly. If it's a switch, the switch will do the job. Again, look up the table of this switch, and then decide which port to forward to the destination. So the idea here is, if you don't know where if you haven't seen this adapter card, this MAC address, you fraud. So you can still cross the boundaries. Okay, there's a sidebar on store and forward switch and cut-through switch. It's not important issue anymore, but it was a hot topic at that time. It says that for a frame to be switched, if you use a store and forward switch, it means that the frame needs to be received completely before it can transmit. So if I receive the frame from this port, I receive the frame completely, and then I look up the table and then transmit the frame. However, in cut-through, it says that if a frame is being received and I have the header already, so I can look up my table and then decide it should be switched to this port. So before I receive a complete frame, I might be starting to transmit. Then, so I'll be doing this, receiving, in the meantime, transmitting this frame. So it's cut through. It will save some time. So it may transmit a frame before receiving completely. As long as I receive the header of the frame, I know its destination MAC address already. So I can look up the table, and if I'm fast enough, I might be transmitting before I receive the frame completely. So it's cut-through switch. So the latency will be slightly smaller, but it's not possible for broadcast frame. And might be too late to check FCS. See, I'm forwarding, I'm cutting through, and if at the end I receive the frame completely, and I check the FCS and find out it's error, then it will be too late because I already sent out a frame. Okay. So it's less popular in the market, and eventually it disappears. So, but it's interesting to see that at that time, some vendor promote the product, saying, okay, our switch is a cut-through switch, and it's much faster than the store and forward switch. And indeed, some user buy in. They'll be convinced. They were convinced that the cut-through switch is better. But I would say, but we would see that it's not a big issue. If you say, I can I can go to the I can if you have a product saying okay, it would make you having your breakfast faster by 3 seconds. Then you would say that would you buy that? It would eat breakfast say 30 seconds faster. It doesn't help, right? You wouldn't buy that because you probably spend 15 minutes. So if it's 30 seconds faster, it's not a big deal. But if it says it could make it faster by 3 minutes, then it's a big deal. You shorten from 15 minutes to 12 minutes. So you cut 3 minutes, then it's a big improvement. But if it's only a small improvement, then you don't care. And cut-through switch is something like this, that the overall delay from the station to that station, from the client to the server, for example, you need to go through the software latency and the hardware latency, and then transmit it propagation time, and then forward it here, and then forward it there, and then eventually reach the destination. And probably the overall latency is say 200 milliseconds or 100 milliseconds, for example, or maybe less, say 20 milliseconds. And 20 milliseconds will be the latency you have. But the cut-through switch could improve, say, from 20 milliseconds to, say, 90 milliseconds or 80 milliseconds. Would you care? No, you don't care much. But it has slight improvement, but some concerns here. For this, you can do that. For this, you might get into error. So you eventually abandoned. So that tells us something, that if you are optimizing something, improving something, the improvement should be significant. If the improvement is minor, insignificant, then it's useless. Sometimes you improve 10%, it's a big deal. But sometimes in some area, 10% improvement is not a big deal. You probably need 50% improvement to be significant. Okay. Okay, look at the open source implementation on self-learning bridging. And so how is the table implemented? So the big issue is you need to check the source MAC address and also check the destination MAC address. You check the source MAC address in order to do self-learning. You check the destination MAC address in order to do forwarding. And if you check the source MAC address, you check whether you have this entry. If you don't, then you insert. So if there's a frame with the source address of this, you want to do self-learning, so you put it into a hash table, a hash function. A hash function, this is the hash function, and then into the hash table. So suppose this entry, and then you do comparison. If it's no match, then if there's a linked list here, you do the comparison again, and until you match, or until the linked list is exhausted. Then if no match throughout the linked list, then you know this, I have never seen this MAC address. So I would insert here. I would insert at the tail of the linked list. So this is a new MAC address, and I need to learn it. However, if this is a match here, there's a match here, so this is not a new MAC address. So I have known it. I have learned it already. However, here I need to refresh my timer, because the table here, each entry has a timer and that to expire. So I need to insert the table entry. And I need to update the timer. So update the timer here to refresh the timer, saying, okay, this is recently learned. If the timer expired, then the entry will be removed. Okay, so that's self-learning. So again, it uses a hash function and hash table to do the job. Okay, and there's one problem with the self-learning. If you have a topology of this, and each of these are switch. Each of these is a switch, and you got switch interconnected together. Then what happens is that there are loops. So it's possible if a station here, if there's a station here, sometimes it goes through here to reach this. Sometimes it goes through this. So for this switch, for example, for this switch, it will be confused. Okay, for the station of a MAC address of this, last time I saw it from this port, say port number 2. Next time I saw it from port number 13. So I have confusion. I don't know. This guy sometimes come from here, sometimes come from there. So it's a confusion. In the worst case, I might be sending to this one. It's possible that, okay, if for this station and this switch, sometimes it's from this port, sometimes from this port. And if I send it to this, and this switch think that for this switch forward a frame to this, but a switch says that, sorry, there's scenario. It's possible that the frame will have temporary looping before it can reach the destination. And so in order not to confuse the switch, we would need to impose a spanning tree, a tree that would eliminate the loops. Okay, so you can see many loops in the topology, and if you disable, say, the port that have the cross, the red cross, then if you disable those ports, then it becomes a tree. And how do we do that? How do we eliminate the loops, impose a spanning tree? And you need to run a distributed protocol, which is called spanning tree protocol. And it's distributed in a sense that no one is actually configuring this, and there's no central point. If one switch fails, the tree can still be formed and could be adjusted. And then when we talk about a tree, you will need to decide the root of the tree first. So the first thing is that every switch will send hello message with ID, with its ID, and the switch with the smallest ID will be the root. So all the other switch will shut up after they receive a hello message from this switch, because it has the smallest ID. Okay, so it becomes the root. So the other station would know this guy is the root, and here's the ID of this. And it would also know the root port the port that would lead to the switch. So they would know the root port. Where is it? They would know the root port through the switch. And then the next thing is to disable some port to eliminate the loop by choosing the designated port, DP, designated port. And the way to choose the designated port is by this. For each switch, the designated port is selected as the port with the lowest path cost to the root. For example, this switch would not take care. It would not take care of the traffic from this side, because they have a tie. They have a tie to the path cost to the root. They have a tie to the root. I mean the path cost. So and when they have tie, they would disable the one with the higher ID. So this switch has higher ID than this, so they disable this port. So that would eliminate this loop. There was a loop here, but this port was disabled, and then the root loop is eliminated. So by doing this, they would choose, they will break the loop. So for example, for this one, the same, this port will be disabled. So by running this distributed protocol among the switches, they would decide the root switch and then root port of each switch, and then the designated port for each LAN. Then the spanning tree is formed. And again, if this switch fail, then because these exchange distributed protocol is run in the background continuously. So if one switch is lost or removed, they would readjust the tree topology. They would have the new root. They would have the new root port and then the new designated port to form the new tree. Okay, then no loop. However, the disadvantage of using a spanning tree is that if two stations are here, one is here, one is here, and they want to talk to each other, originally, if this port is not disabled, then the frame will go this way to reach the destination. So it would not travel too far. But now it needs to travel this far, go up, and then go down. Go up and then down. So that would and for example, if two stations, one here, then what happened is that because this port is disabled, so it will go this, and then go down to reach the destination. So you need to traverse a longer path to reach the destination if some ports are disabled. But perhaps we would say that it's not a big deal because it's a LAN, not a WAN. If it's a WAN, it's no good because you travel to US and then go back to Asia. That's a triangle routing. But triangle routing on LAN is not a big deal because it's only a short distance. So you can afford that kind of triangle routing. Okay, the open source implementation here, you will see the root port selection. They select the root port. They select the root, okay, and then select the port, including the root port and designated port here. And it's inside these functions. And the final topic on bridging is VLAN. virtual LAN, the idea is this. If without VLAN, you have, say, four switches, then each of the 4 switches will be a what? A broadcast domain, right? 24 ports form one single broadcast domain. Okay, and if it's a switch, then you got 24 collision domain, but only one broadcast domain. And this will be one broadcast domain, another broadcast domain, another broadcast domain, another here. So 4 broadcast domain. But there are needs that saying, okay, I need to have this switch and this switch, certain port of this switch combined with this switch to form a broadcast domain. Say some port here and all port here form a broadcast domain. If I want to do that, and also some port here to form a broadcast domain with this one, and some port here to form a broadcast domain with this. So I want to cross switch. I want to have cross switch broadcast domain. Cross switch broadcast domain. Then I can only do that by VLAN. So VLAN says that you could configure some of the port here with some of the port here to form a broadcast domain, which is a VLAN. It could cross the boundary of switches. Okay. So I can divide a switch into several broadcast domains. I can combine different switches into a broadcast domain. So these are the advantages. But the question will be, why do I need to do that? Why do I need to do that? It happens that a financial department, so for example, it says that the financial department has used 1.5 switch, one switch and another health switch. So they need to they need to form a broadcast domain in order to run an application, for example. Then they need to form one broadcast domain. So then I would need to have VLAN. You can say, okay, why not just buy a larger switch for the financial department, or buy two switches, one big switch for the sales department. Okay. Then if you do that, then you can solve the problem, but it would lose the flexibility of configuration the broadcast domain. So if you consider this as, okay, the VLAN 2 is the financial department, the VLAN 3 is the sales department, and this is the marketing department, for example. Then and because they need to keep their frame inside their department, they need to run specific applications, so they need to be within the same broadcast domain. But you don't want to change the physical wiring. You don't want to change the physical wiring in order to put them into the same broadcast domain. So you do the configuration on VLAN. So that's the idea. And configuring VLAN could be mostly done by port-based. You specify the port here. But sometimes you can specify others, say MAC address, IP address, or applications. But these are advanced features of VLAN. Mostly you just use port number. Okay. And that VLAN standard is specified in 802.1q. 1q. Here are two figures that you want to form a VLAN. Okay, if this is two switch, here are two subnet. You have two network. and each connect to a switch, and then cross the router. And if you have this, if you have two subnets, the idea of subnet will be explained further in the next chapter. But here you see, if you have if these 6 stations are connected to the same switches, and then connected to a router, if this switch does not have a VLAN, then all the 6 stations will be in the same broadcast domain, right? They'll be in the same broadcast domain. Then they will be, the idea of subnet is also the broadcast domain. So then you are putting 2 subnets in the same broadcast domain, then it's not what you want. You want them to be 2 different broadcast domains. So this is one broadcast domain, this is another broadcast domain, but connected to the same switch. But then you destroy the nature, then they belong to the same broadcast domain. So what you want to do is that you want to configure the VLAN on this switch, saying these 3 are one VLAN and this another VLAN. And they form 2 broadcast domains, even though they are connected to the same switch. Then this is a so-called one-armed router. One-arm router. This is 2-arm router. 2 router. With this configuration, you need two switches. Okay, but with this configuration, you need one switch, only one switch with VLAN. Then you can separate. Then you can separate them into 2 broadcast domains. Okay, but if you have configured VLAN, the frame sent need to have an extra tag, which is called VLAN tag. Okay, there are 2 fields. One is called VLAN protocol ID, which is a fixed number, and then a tag control with a priority and the VLAN identifier. So you need this and this to identify, okay, which VLAN it belongs to. Basically, you need to identify which VLAN this frame belongs to for the switch. With that, the switch will know where to forward the frame to. Okay, some other standard like link aggregation, saying, okay, if a switch, it's another standard called 802.3AD. It says that if you want to connect two switches, but each line is only 1 megabit per second, but you need to have connectivity of 400 megabit per second. And you need 4 lines. Then how do you use 4 lines together? It says that this standard, link aggregation standard, would do the load balancing among multiple links between two switches. So if the switch support this standard 802.3AD, it would do the load balancing among the multiple links. So what it does is, if I have a frame, I would send it to this link. I would do, say, round robin to send the frame, and then receiver will receive the frame. So the purpose here is I want to send faster. The 100 megabit per second is not enough to carry the traffic between these two switches. Then I would need to use link aggregation.